Hello people, how you guys doing? It is Abjoin Babatunde Kupola for this channel, Nubra Preset Designer. Hope you are enjoying our video. If you have been watching, you can actually encourage us to do more by sharing our video and liking it so that more people will be able to see. And if there is something that you want us to work on, you can always get in touch with us through our contacts. I think from the beginning of this video there is some contact information that you can chat up or call. You understand, we are always available to discuss with you. So today we are continuing from where we stopped in the previous video on the shortcut binary distillation modeling with Excel and VBA. So in the first video we work on the material balance of the whole distillation column, and for the major stream, the vapor and the reflux flow in the rectifying section, while the boil up flow and the liquid flow in the sweeping section. And we calculate the bottoms and the distillate products flow, you understand, based on the reflux ratio specified. So I'm using a placeholder for the minimum reflux ratio because my reflux ratio is based on my minimum reflux ratio. But when I was using 1.5, the reflux ratio is too low, so I'm getting negative flow in my colon, so I had to override the reflux ratio to be 2.5. You understand? So, and today we are going to be starting with the feed quality calculation. So I'm going to be discussing more on the feed quality today. For the to get the feed quality, we need to get the vapor fraction of the feed, that is the temperature. We need to get the vapor fraction of the feed from the temperature of the feed. Although you can see from the yellow box here, we have the temperature of the feed to be 95 degrees Celsius. So the quality will depend on this temperature. So we have to flash the feed, that is get the vapor fraction. So that's the major thing about feed quantity, of the feed. So we have to get the quantity, the thermodynamic condition of the feed. Maybe it's your subcool liquid or saturated or mixture, or like a superheated or vapor, you understand. So we need to get the condition, so that we can do that by flashing the feed. So to do the flash calculation, I made some presentation on it. So flash calculation is just like when you have a system, a mixture of two or more. So because we are making a simplified system, so we are only doing with a mixture of two. So let's start from this place. Okay, this is what we call the vapor liquid equilibrium of a binary mixture. That is, this is what relates the behavior of binary mixture, you understand, when you heat it up. For example, if you are coming at a very low temperature, let me show you something. This is something that I've done. So if you are coming, like for example, you have a low temperature in this plot, you understand, and this, the axis at the bottom, the horizontal axis, is the composition axis. So for example, you pick your mole fraction from this axis to be 0.45, like what we have done in the Excel sheet. The mole fraction is 0.45. So as you keep on increasing the temperature of the mixture, the temperature will keep on increasing, you understand, so until you reach the bubble point of the mixture. So this is what they call the bubble point. This point over here is what they call the bubble point of the mixture. The locus at this bottom is the bubble point locus, while the locus on the top is the dew point locus. So when you reach the bubbling point, assuming it's a pure compound, it's going to stay in that temperature until the whole substance is vaporized. But since a mixture of two or more pure components with different boiling points, you understand, so that means the temperature will keep on increasing. And the meaning of this bubbling point is the point when you see the first vapor in the mixture, you understand, and the first vapor in the mixture will correspond to this to this point, you understand, and this point will be the saturated liquid point, you understand. So the liquid will be having the same mole fraction, while the vapor mole fraction will be higher, because in this plot is correspond to the lighter component, you understand. So more light component we want to vaporize in the first instance, you understand. And as you keep on increasing the temperature, the temperature will keep on increasing, and the vapor that is being formed is going to be reducing. The mole fraction of the vapor is going to be reducing in terms of the lighter component, while the mole fraction in the liquid will also be reducing until it reaches this point, you understand, until it reaches this point, and the vapor will reach this point, that is the same point that is starting from in the subcool region, because this is where you call the subcool region, and this is where they call the dissipated vapor region. So that means, all when it reaches this point, this is where we call the dew points of the mixture. That is where the first liquid we drop if you are cooling down from high temperature, you understand. But now we are eating from low temperature. So when you eat the mixture to a higher temperature, you understand, and it reaches the dew point of the mixture, you understand, then you are going to be having the last liquid composition, and this liquid composition will be very low compared to the initial composition that you have for a lighter component, because more heavier components we want to stay in liquid state. So that's the idea of this plot. And I'm not going to be using graphical methods to calculate this dew point and bubbling point, because I need this dew point and bubbling point in order to know the states of the mixture. So if the mixture is at lower temperature compared to the bubbling point of the mixture, that means it is in the subcool region. So if the mixture is in between the bubbling point and the dew point, that means it's a saturated mixture, you understand. So it's having two phase, you understand, that is liquid and vapor phase. So if it is above the dew point of the mixture, then it is in superheated region. So I need to know these two temperature point of the mixture based on the period, because this is like in 1 atm, but the one that we are actually working on is in 1 bar, but we just consider it one after the other. So we are using two theory, chemical engineering thermodynamic theory, the Raoult law and the Antoine equation. The work of the Antoine equation, like the one that you have in the result sheet over here, these are the parameters that we are using, is basically what I had there. So it's to calculate the saturated vapor pressure of pure compound, you understand. But because for our mixture we are having benzene and toluene, so it's going to calculate the saturated vapor pressure, you understand, at the temperature of the pure compound. So we are going to do that for the two components, while the Raoult law relates the partial pressure of the system vapor to the saturated vapor pressure and the liquid mole fraction. The yi is the vapor mole fraction, while xi is the liquid mole fraction. So we are basically using these two equations to get the dew point and the bubbling point. And the calculation for the dew point is starting from the Raoult law. So the assumption is like, in the mixture, when you're having a mixture, for example, let's go to this place. When you're having a mixture, you have vapor in the mixture and the liquid in the mixture. For an ideal mixture, you understand, the pressure exerted by the vapor must be equal to the pressure exerted by the liquid. So for the equilibrium of forces, like for the system to be in equilibrium, that means the partial pressure of the vapor of that component in the vapor phase is equal to the partial the liquid pressure, saturated liquid pressure that is coming from the liquid phase, you understand. So that's just the idea on this equation. So, and because this is a sequence equation having the amount of component that you have, so if you have like 1000 components, that is Raoult law is going to be is available for them, you understand. So you can write that law for each of the components. So when you sum up all those components, that is summation y pi, then you it's going to be, you sum the both sides, you understand, for all the components. So because pressure is constant, like this pressure of the whole system is constant for this, like yi is the mole fraction in vapor phase, and when you multiply with the p, you get the partial pressure, you understand. So you can substitute, you can remove pressure out, you understand. And from, when you sum all the mole fraction, for example, even if you're having like two binary compound, you understand, that means the summation of all mole fractions should be equal to 1, you understand. So that's why summation yi is going to be 1. So you have something like this: p is equal to summation pi x. So when I did this for the binary mixture, so we have it's going to be p1 x1, p1 sats x1 plus p2 sats x2, you understand. S2 is going to be equal to 1 minus x1, you understand. So that's where I'm able to get this p2 sats x1, p1 sats minus p2 sats. So the implication of this is like having this equation, I can know my p2 sats from the Antoine equation, and p1 sats from the Antoine equation, you understand. And the mole fraction can be from the mole fraction of the feed is already known to be 0.45. So the next thing I need is the temperature. That will be the saturated temperature of the mixture, and that's what I'm looking for. So I'm going to make my P to be pressure of the system, you understand. Then because this question can be solved like analytically, because it contains natural logarithm and different values of t, and you can see it's very complex to solve. So I'm using a tool in Microsoft Excel to solve the equation. So what's the tool? I'm using a GoSeek tool in Microsoft Excel to solve the equation. Okay. As we are done with the bubble point, I would like to explain the dew point, also the dew point calculation, because you can use this for the dew point, because like I said, xi is the mole fraction in liquid phase. If you put the value of our mole fraction over here, you understand, because the total mole of the system is this 0.45. So if you put this to be 0.45, you understand, the temperature that we are getting here will be the bubbling point temperature. So for the dew point temperature, we can do the same calculation, but right now we try to remove the mole fraction in liquid phase. We try to remove it from the equation. So for the dew point, we are trying to readjust this equation, that is making xi subject of the formula. So we have yi pi sat is going to be equal to xi. Then I find summation of both sides, saying you have the summation xi is 1, you understand. Then from here you can see that p will be equal to, like, trying to divide both, or find the divide both sides by p, then finding the inverse of both sides, or you said divide both sides by summation yi pi sat, sorry. So then you have this. So then when I did it for binary mixture, try and do just to simplify the process, then you have this equation for the binary mixture. So this is equation for the dew point, this is equation for the bubbling point, you understand. So the what I did there is just to do one for dew point and do one for bubbling point, and you can see from here this will be the y1 L, that is the mole fraction in vapor phase for dew point, while this will be the xip, that is the mole fraction in liquid phase for bubbling point, you understand. So I have to make this mole fraction that I'm getting to be equal to the real mole fraction from the feed, you understand. So that's meaning of this difference. So the next thing that I'm going to do after doing it is to change to iterate, because the GoSeek function can be used for iteration, you understand. So it can produce mathematical results rather than results that are physically because we cannot solve the equation with analytical method, you understand. So we have to iterate the value of the temperature, that is this temperature in this equation is going to be iterated, like it's going to be adjusted, you understand, till we are able to get for example, for dew point, we are able to get the same mole fraction for the feed. You understand? So that's what we have in this place. So the mole fraction that I'm getting here, assuming I start, I put a value for the temperature. Let me put 100 for the temperature. Once I put 100 for the temperature, I'm going to do for the dew point first, but I've already written the equation here. So this is from the Antoine equation. You can see exponent is e raised to power. So this is like making okay. So this is P1 start. Okay, this is the equation over here. Okay, because you can see all the Antoine parameter has been highlighted. So this is like writing, because we have a lane, you understand? So you have to find the exponent of both sides to make P1 side solution of the formula. You're looking for P1 side, and the 100 that is there is just to convert it from kilopascal to bar, because I'm doing my calculation in bar. You get it? So then for the second one, I don't want to be writing the formula over and again. Yes, so I did the calculation. I copied the value from the second one. So we have for the second, that is saturated vapor pressure for the second component, that is toluene. So this is the value, and you can see the value for the temperature is D50. So you have to make the where's D50? Okay, so that's the value for the temperature. So you have to change it to, because temperature is in degrees Celsius, so I have to convert it to Kelvin. That's why I have to do 73. So I'll change the value for this temperature to be this TV. So that's all the thing that I will do to edit the formula. You understand? So that's all the temperatures value. I think you're having three temperature values. So just to cross check, T, so it's three temperature values. Okay. So I'll do for the second one too. So we have this. Oops. Do for the second one too. Just copy, change the value of temperature. So once we have this, this is the value based on the temperature of the temperature that I'm trying to use to calculate my dew point. So the next thing is to write the formula for the YI feed, that is the the vapor phase mole fraction. You understand? Because from these plots, our vapor phase mole fraction must be equal to the same mole fraction that we are starting from 0.45. You understand? So I'm going to copy the formula from my. So this is the formula that I get 1 over P. This the 1 over. I'll show you when I'm. So we have the 0.43. So that means this is the formula for the. So it's based on D36 is the saturated period of the second component, while the D35 is saturated period of the first component. So we have 1 over D36 and 1 over D35 minus 1 over D36. That is when you solve this formula over here. You understand? Then you have okay, so you make y the subject of the formula here. When you make yi the subject of the formula, then that's the value that you are going to get. So then once we have this, then all our equation has been set, because each cells are now connected to each other. You understand? So we can be changing the value of this temperature, and to make sure that this 0.45 is the same thing as the mole fraction that we are getting. You understand? So then we can be rest assured that that temperature is the saturated dew point, that is the dew point temperature of the mixture at this composition. You understand? So I'm going to go to the you can get to the GoSeek by going to the data tab, then the what if analysis, then you go to the GoSeek, then you pick the cell that you want to set the value to be equal to 0. So this difference is the difference between this 0.443, that is the mole fraction, vapor phase mole fraction that we are getting, and the Way mole fraction of the feed. So I'm going to set it to be 0. Then the cell that I want to be changing is the dew point cell. So it's going to run the analysis, and it has converged to 0. So this will be my dew point of the mixture. So you can see this is now 0.45. That is the same thing as the mole fraction of the feed. Then we have the difference. You can see F16 from the differences. Okay, this is the difference. That is, this is the feed mole fraction and D35. This, then I multiply by a large number so that it will be very close to 0. You know, sometimes when the difference is like 0.0000, you understand, it will take it as 0. So when you multiply to a large number, it will be able to make it to be the tolerance to be higher. So then I'm going to do the same for the bubbling point. So for the bubbling point, I'll copy this to formulas. So once I copy the formulas, we have this. So D40, and it has changed the temperature to D40. Then we have D40 over here. Then this one is also D40. So I can create an estimate of 100 degrees Celsius. So if it's 100 degrees Celsius, then I'll put the formula for the bubbling point. So this formula for the bubbling point, that's what I'm going to use for X. That is making X the subject of the formula, and it is already in these formulas I've written before. So we have the bubbling point equation formula like that. So I'm going to put the bubbling point formula over here. Okay, so this is the bubbling point formula. So it's going to take this is O16 is the pressure of the system. You can see O16 is the 1 bar. You understand? So it's a isobaric process, that is just one pressure process. You understand? You can see the difference is very high now. You understand? So, and this difference is F16 minus this 37, that is the same mole fraction. So we are going to do the same GoSeek for it too. Okay, let me not do it again. This GoSeek, I've written it in the code, so I don't need to be doing it over and over again. And you can get the code from okay, this is the code that I wrote for it. You can see temperature, iteration. So I'm just going to be pressing code. So the meaning of the GoSeek is just to run the GoSeek function on series of cells. You can see it's going to change this, or it's going to make this value to be 0, just like what I did. You understand? Then by the changing cell, I've already named the changing cell over here. You understand? So I'm just going to run the function. You understand? So that to make the work faster. So once I've run this function, you can see that it is now 0.45. You understand? So that's that on the dew point. So you can calculate the dew point and the bubbling point of any mixture through this algorithm system. You understand? So the dew point is this 99.43, while the bubbling point is 92.28. Just be careful so that what you are getting is, it's supposed to be, dew point supposed to be lower or to be higher than the bubbling point. You understand? So if your own bubbling point is higher than your dew point, then something is wrong. You understand? So then the next thing is to get the real PSAT, saturated vapor pressure, and saturated liquid pressure of the feed at the temperature of the feed that we are having here. You understand? So I'm going to, because we needed to get the dew point composition and the bubbling point composition of that mixture, because the idea is just assuming the mixture is in between the dew point and the bubbling point. You understand? So, and in between it is also, because there's not going to be there is nothing at the center of this loci You understand? So, and we're having the, this is the bubbling point. We're having the bubbling point here. So if the temperature is higher than this, so it's going to be in another mixture. That is, let's just say this line over here. You understand? This line over here. You understand? And it's going to have its own bubble point composition and dew point composition. That is, the liquid will contain lower light component, while the vapor will also contain lower light component as moving closer to this point until it reaches 0.45 again. You understand? And this, the liquid or mole fraction, which is this point, you understand, around the 0.223 or something. You understand? So, and the formula to calculate those liquid mole fraction and the vapor mole fraction has been already been given to us through Raoult law. You understand? So it's actually quite easy to do. So I need to just get this piece out based on this temperature, because I can change the temperature to any temperature I like. You understand? So that's the next thing I'm going now. So I'm going to copy this and paste the formula here. So I'll just change the temperature to the temperature of the feed, which is this F17. So I'll change all the temperature to F17. So we have this. So why I will do it for the second one. Okay. So once I'm done with that, then I'll just calculate the dew point mole fraction and the bubbling point mole fraction. So to do that, I'm going to use this formula over here. So, but this is just the same thing as these two y, I, f, and w, but this contain if statement. And the reason why it contains if statement is when the temperature is low, you don't want to. The reason why it contains if statement is like when the temperature is lower than, once you have calculated your dew point and bubble point, because when I told you when the temperature is lower than the dew point, the mole fraction of the mixture will remain the same. The mole fraction, nothing will change the mixture, no material balance. You understand? But when you are in between this, you are in saturated point, in between the saturated vapor and the liquid point, you understand? Then that is when the mole fraction of the liquid and the vapor will be changing. You understand? Will be different. You understand? So that's the reason for this if statement. So if the temperature is lower than the dew point temperature, you understand, is going to make the vapor phase mole fraction to be 0. You understand? And if the temperature is higher than, is in between the dew point and the bubbling point temperature, you understand, that is, if the temperature is still lower than D7, D37 is the dew point temperature, then it's going to use this formula to calculate the vapor phase mole fraction. But if it is higher, it's going to be the mole fraction of the feed. You understand? That is, at this point, the mole fraction will keep on increasing. So that's the meaning of the if statement over here. So for the dew point, that's the same thing. So we have the dew point lower. If the temperature is lower than the bubbling point, it's going to use the mole fraction of the feed. You understand? And if the temperature is higher than the bubbling point but lower than the dew point, it's going to use the normal mole fraction for the liquid phase or liquid phase. Then if it is higher, it's going to be 0. That is, there is no liquid phase. You understand? So the last thing on this vapor fraction is just to calculate the fraction of the vapor in the system. And to get this formula, I just have to use the material balance on flash calculation. So to do that, I did something on this section. Okay, so for this section, assuming we have like binary mixture of the, in a system, in a closed system, then we have the feed F, then Z, that is the Z of the flow into the system. You understand? So the overall material balance F is equal to V plus L. Then the component, lighter component is, let's just say this lighter component, Z of is going to be equal to YV plus XIL. You understand? Then the vapor fraction is going to be vapor over liquid, that is the fraction of the vapor in the liquid. So the idea is just to make this be the subject of the formula. Once you know the Z, you know y, that is the mole fraction in the vapor phase, and you know the mole fraction in liquid phase. So solving this equation for vapor fraction, you are able to get this value for the vapor fraction. So that's I did the formula. So the next thing is the enthalpy. So because the major reason why we are doing all these vapor fraction calculation is to get the feed quality, and the formula for the feed quality is given here, that is enthalpy of the feed minus enthalpy of the saturated liquid of the feed at saturated liquid condition, then the enthalpy of the feed at saturated vapor minus enthalpy of feed at saturated liquid, that is just like the heat of preparation of the feed. You understand? So so I need to get this enthalpy of the feed and this value and this value. So to get that, and I have the formula for the enthalpy of the feed here. So this formula for enthalpy of the feed is a pretty big formula, although I try to make it lower by using what we call VBA function. So the idea is like, okay, from here we can start from here. The idea is like writing the using its capacity parameters for each of the pure components, and using their mole fraction to get their contribution to the heat capacity of the mixture. Then we have this TB is the temperature, that is the boiling point temperature of the mixture. So this is the reference temperature. So the heat capacity at boiling point, you understand this, that's the meaning of CP lake 1 TB. Then CP lake 1 T ref is the heat capacity at reference point. So you do this for the subcool region. Then for the other region, because you need to know if the system is above bubbling points or above dew point, you understand. So if the system is above boiling points, you are going to need the heat of vaporization of the system, and that's why you are having the vapor fraction. So if the vapor fraction is 0, then you don't need the heat of vaporization of the system, because there is no vapor in the system. It's still below it's still in the subcool region. So we are not, so that's why I put this vapor fraction for this. So the vapor fraction is multiplying all these other equation. Then you have the last term for the vapor heat capacity of the vapor, you understand, starting from the it's going to start from the dew point, you understand, the temperature of the system. So if the temperature is greater than the dew point, this equation is sufficient to calculate the enthalpy of the mixture, you understand. So, and that's why that's what we are having here. And the another thing that I would like to mention is my heat capacity is written in this form. A, that is this is the function for the heat capacity, and you put the parameters over here, you understand, and you can adjust the parameters that you have, you understand, to fit in this parameter in order to use this this model to calculate for your work. So to reduce the length of the equation, I have to summarize some of the function in what we call the VBA function, and that's what I've shown. Okay, that's here, and that's what is there in the function CP. Although I'm not really using this MH again, so CP is just using the same thing that I've written. So you can see Z is a composition, y T is the temperature of the system, and P is a parameter range of this parameter range that you are using, you understand. So we have the mole fraction, you've specified the mole fraction that it is going to use. So this function will take in the mole fraction of the light component, binary light component, then the temperature of the component, and the parameters, you understand, to return the CP value of the mixture at the temperature. So that's that. So then the next thing is for the vapor. So Although for this one we are having if statement. For the enthalpy of the feed we are having if statement because of the condition, right? This is the same thing as the Vapour fraction, or the y the vapor mole fraction and the liquid mole fraction. You understand? The meaning of the if statement is like when the temperature is lower than the bubbling point. You understand? The calculation should stop at the bubbling point region, while in between the bubbling point and the dew point, it should stop in the saturation region. And if it's greater than the dew point, should continue in the superheated vapor. You understand? So that's what the meaning of the if statement. So you have the temperature of the system is, of the feed is lower than D 40, and this is if the temperature of the feed is lower than the dew point. You understand? So it's not going to include all these calculation for the dew point's contribution to the enthalpy. So why this is for the vapor? You understand? For the vapor, so we have the enthalpy from the to the feed, then the heat of vaporization. You understand? So it's going to do this at the temperature of the system minus reference temperature, then the the enthalpy of vaporization contribution. You understand? So then we have the liquid, saturated liquids of the feed, then the heat of vaporization of the feed. So with this we can, yeah, we can easily calculate our with this we can easily calculate our feed quality. So the formula for feed quality is this. Just other the because to I'm going to explain this once I copy it. It's using the same process and technique to just to prevent, because these values are not like your mathematical. They are realistic value. You understand that? Like, so you have to be very careful when you are doing the calculation. You understand? So the case is like if the temperature is lower than the dew point temperature, you understand, the quality will always be one. So if the temperature is only within the range of the dew point temperature and the bubbling point temperature, then that's when this equation is going to be used. So then if it is greater than the dew point temperature, it's going to be 0. So that's the meaning of the if statement. So you can see we are now having a new feed quality. So then it takes us to this section. So this section I calculate the the saturated temperature of the pure component of both components, the benzene and toluene. You understand? Because I'm using it to just to check, to proofread my model. You understand? So just so if I'm working out of line, I'll be able to see it. You understand? So and the thing is just to have the period of the system 1 bar and just copy the formula. Like, thing is to copy the formula for the okay. Okay, so this is a very large number. We can just change it to 100 over here. So this for the second component. So it's going to be having different um different temperature. So this is going to be D50. Oops. Okay. We'll bring this one to 100 too. Then I'll make this one D50 and this one 50, and this until 50. Okay, so I've done it. So the idea is like we have to get, because this will be our saturated pressure. So to get the saturated temperature, because what's actually governing the saturation is the pressure and temperature, you understand? So we have to make our pressure to be equal to 1 for both the components. Without none of this difference, that is the pressure of the system and this value, you understand? Then this is the pressure of the system minus and this value. So we have to make these two values to be equal to 0. You understand? So, and we are using go 6, so I'm just going to run it. Then it will just make them to be 1 1. So the value difference is 0. So this will be our saturated temperature for the first component, that is benzene, at 1 bar, and this will be the saturated temperature for the second component, or toluene, at 1 bar. So it corresponds to this value over here. This is for the heavier component, this is for the light component. Okay, the light component should boil at lower temperature, while the heavy component will boil at higher temperature. So we have we are done with that section. So the next thing is to do for the stages temperature. For the stages temperature, we are using the normal rotation, that the stream that is leaving the stage is coming as saturated stream, not subcooling or superheated, you understand? So we can, if they are coming as saturated, maybe it's a liquid stream that is coming from a stage and it's saturated, you understand? So from the composition we can get the temperature of that stage, you understand? So because the, like what we have done for the feed composition, you understand, we just do for the each stages liquid flow that is coming from that stage. So, and because we are having more fraction, the composition that is coming from this, from the condenser over here, you understand, is going to be having 0.08806, you understand? So we can get the temperature of the condenser, you understand, because it is saturated liquid that is coming, you understand, there is no subcooling in the condenser, you understand? So, and we just copy the formula for these two, then we are going to put it in the condenser. Then we change the temperature to the temperature where we want to be using temperature of the condenser. So this temperature of the condenser, I have to change this value to, okay, let me change all this value to 100, just as starting temperature. And because I'm running the go seek, that's why the temperature is just changing. Okay, so although now I'm going to run it at the same time, so I'm going to change this one to the temperature again. So this is the temperature of the condenser, R15. So for this, I'm going to change it to R15 too. Okay, so we're done. So the next thing is just to copy the formula for the liquid mole fraction. I'm looking for the shortest formula to copy because I don't want to. Okay, let me copy this. So let's just copy this here. So we have something like this. 35, 36, okay. So 36 is 35, and this will be 36, and this will also be 36. Okay, so we are having this and this. So I'm going to do go seek. I'm going to run the code, and you can see we are having the value to be 0. So the temperature that I got here, that will be the condenser temperature. So I'm going to do I'm going to do for the reboiler, and the assumption is for the reboiler is this the mole fraction, you understand? And for the first top stages, because you're having a total condenser, you understand, so there is no partial saturation, you understand. So it's just like having these two sections over here. What is coming here, so the mole fraction is the same thing as the mole fraction for the that is coming in. No, we are pulling from the condenser, we are coming down from here, you understand. So the mole fraction does not change, so we can still use the same mole fraction of the distillate for the vapor that is coming, but it's going to be a dew point temperature of the composition, not the bubbling point, because it is vapor phase. That is vapor that is leaving the stage, you understand, the system is at dew point, you understand, while the liquid that is leaving is at bubbling point. So we are going to do that for that. So I'm going to skip the video so that's not to make this video to be very long. Okay, so for this, I got the temperature of the boiler to be 99.33 degrees Celsius, while the first state temperature is 87.50 degrees Celsius. So remain the last stage, which is the bottom stage. So the idea for the bottom stage is, because it's the boiler is a boiler, so there will be heating to be done, more like a condenser. Like if you are, this is what you do when you're having a partial condenser too. So because we're having a total condenser, our work is much easier, you understand. So for the condenser, you're having feed that is coming to this condenser, F or FZ, then the vapor at more fraction of vapor phase. This is the, let's say this is our vapor boil up, and this is our bottoms that is coming at the bottom, you understand. Then you're heating up the vessel, the boiler vessel. So the material balance doing the same thing for this system too, you understand. So from the Raoult law, you have the y, that is for the equilibrium, vapor liquid equilibrium of this mixture, you understand, is going to be Raoult law, you understand. So you can make y the subject of the formula, that is for the light, let's do for the light component, that is benzene. So if you make y the subject of the formula, you have yp is going to be pi site p sat, then x, you understand. So then for this, you can substitute this mole fraction in vapor phase into this equation. So once I substitute this value here, then I'm able to solve for the value of mole fraction that is coming in. I've just divided both sides by the total flow, that is the liquid flow to the boiler, the stripping section liquid, you understand, that is going to the reboiler. So that will be the F. So I'll be able to get the mole fraction of the light component that is coming to the reboiler. So that's the what I need. So once I have the mole fraction of the liquid that is coming to the reboiler, I know the liquid is coming from the last stage, the bottom stage of the tower. So from there, from the theory that the liquid is saturated liquid, I can be able to get the temperature of the reboiler of the last stage. So that's the idea. So for this equation, I'm going to, okay, let's just copy this formula first. Okay, let's do this. Let's copy this formula first for the, so I'm going to change this one to, this is 18. So I'm going to change this one to the temperature of the last stage, that we can call it today R18. So I'll change this one to R18. R18. So I think I'm done with the value over here. So the next thing is to put the value for the xi time. So this will be my value from the calculation, from the equation. This is the formula for it. So I just put the value over here. So from there you can able to get, you have to p, you can see p1 starts from the equation. You have p1 sat here, then the mole fraction in liquid phase that is coming, which is the 0.025, this value at the bottom, you understand. Then the liquid phase mole fraction, the vapor boil up, you understand. Then you have this value too, you understand. So I will not be going deep into the equation. So then we use the formula for the liquid phase. So for the formula for the liquid phase, I still have to change things. For the liquid phase mole fraction, okay, so I'm going to change this formula. So we have this something like this. So this will be 44. So this will be 43. Just to make the equation to be proportionate, I'll just take it back because I copy it. So this will be 40. Oops, 44. Okay, so we have something like this. Let me copy this formula back. So we have something like this. So I'm going to be changing this temperature so that I'm able to get the same thing for the answer. I just want to confirm something. Okay. Okay. Okay, it will work. So I will run the code and see what happened. Okay, you can see it has now converged to the same value. So the mole fraction that is coming from the bottom of the tower is 0.34, you understand, to the reboiler, the mole fraction of the light component. So and the whole system has now converged. So the next thing is just the enthalpy and the condenser duty and the reboiler duty, and we are going to be doing that in the next video because this video is already long enough, you understand. So see you in the next video. Thank you for staying tuned and thank you for your time. So see ya. Thank you.